Let's look at the noise performance of a pulse code modulated system. So we'll start with a binary signal. We have a string of ones and zeros. In this case, we're looking at 1, 0, 1, 1, 0, 1. The strings of ones and zeros have been encoded in this fashion. Logical 1 is a value of A volts. To be more general, and a logical 0 is a value of 0. So this is a unipolar signaling system, and this is the one we'll look at. The results will be slightly different if you have a polar type system, but this one is the one we'll look at to begin with. So we have the message signal, which is either it takes a value of A or takes a value of 0, depending upon if the binary bit is a 1 or a 0. And we're going to add noise to that binary signal. We're adding noise to the binary signal, and here is a graph of a bit of random noise. And we are looking, as always, at Gaussian distributed white noise, and it will have a power, a noise power. So this is sigma n squared is the power, the noise power, or the power in the noise. And the larger the value of sigma, the larger the noise, the bigger its peaks and valleys. And so if sigma n was very small, it'd be relatively small noise. If sigma n's bigger, it's bigger noise. So we add the noise to the binary signal, and that's shown in the trace at the bottom. And you can see that as you add noise to the binary signal, there is a chance, if the noise is big enough, that maybe the ones will be misinterpreted as zeros, and maybe the zeros would be misinterpreted as ones. Well, if that were to occur, this would lead to a bit error. You would erroneously interpret one of these signals as the other bit, and we need to investigate the effect of these bit errors. Looking at the binary signal that was shown on the previous slide, it has a signal power where you find that by squaring the signal and taking the time average. That's going to be a squared divided by 2. Remember, a logical 0 is a 0, logical 1 is a 1, and they occur with equal probability. So the signal power is a squared divided by 2. The noise power, as we described previously, is simply the variance of the noise, the Gaussian distributed noise. So that's sigma n for noise squared, that's the power. So we can form the signal to noise ratio of our signal plus noise. That's going to be the signal power, a squared divided by 2, divided by the noise power, sigma n squared. So this is now the signal to noise ratio. The noise is Gaussian distributed, and that's shown with this probability density function here at the bottom. The noise has a mean value of 0, and it has a variance of sigma n squared, so its standard deviation would be sigma n. So if you were to sketch the noise distribution, you would give it a mean value of 0, and then depending on the value of the variance, sigma n squared, take the square root, you get sigma n, and you go 1, 2, 3 standard deviations either side of the mean, and the bell-shaped curve is essentially back down to 0. I've plotted the noise distribution here. I've also shown the value of plus and minus a. Now, that's just for illustration purposes. If you change the value of sigma, it would either be more narrow or it would be more broad, depending upon the value of the variance. In detecting these binary bits, we're going to take the message plus the noise signal, and that will be applied to some kind of sample and hold circuit. So at some point in the signal, the value will be sampled, and that sample then will be applied to a comparator, and if the sample is greater than a certain threshold voltage, then the bit will be will be assigned to the value of 1, a logical 1. And if the value of the signal plus the noise at that sample instant is less than a certain threshold voltage, then it will be assigned the logical 0. So there's two possibilities in sending in our message signal. We're either sending a logical 0, which is 0 volts, and if you add noise to the 0 volts, you get a distribution that's described by this first bell-shaped curve on the left, or we're sending a logical 1, which has a value of A, and if we plot the distribution of the signal plus the noise, given that we're sending a logical 1, that will be this bell-shaped curve on the right. And depending upon the value of the variance of the additive noise, these curves will be either more narrow or they will be wider. And we can determine the probability of an error. And our threshold voltage for the comparator, let's put that right in the middle between 0 and A. So that's going to be A divided by 2. And that seems a reasonable place for the threshold voltage for the comparator. So if we are sending a 0, there is a probability that the instantaneous value of the signal plus the noise will be greater than the threshold, and our intended 0 will be misinterpreted as a 1. Or if we are sending a 1, there is a probability that the signal plus the noise will be less than the threshold, and that 1 will be misinterpreted as a 0. Now, each of those cases would be a bit error. And we are assuming, reasonably so, that 1s and 0s are sent with equal probability. So the total bit error probability would be the probability of sending a 0 and it's misinterpreted as a 1, plus the probability of sending a 1 and it's misinterpreted as a 0. But since the curves are symmetric and the probability of a 0 is 1/2 and a probability of a 1 is 1/2, the probability of an error is equal to this area that I've highlighted here and indicated as Q of, this would be V threshold minus 0 divided by the square root of the variance, so divided by sigma n. This area gives us the total probability of a bit error. So for a numerical example, let's say a logical 1 is 1 volt and a logical 0 is 0 volts. So the threshold voltage for the comparator is going to be is 1/2 volt. Let's take for a numerical value that our signal power, well, that would mean if logical 1 is 0, our signal power is going to be 1 squared divided by 2. That's going to be 1/2 watt. For a numerical example, let's take the variance of the noise power, the variance of the noise equal to sigma n squared equal to 0.16 watts. So that would make the square root of the variance. So that's just sigma n is going to be the square root of 0.16. That's going to be 0.4. That's a nice round number. The signal to noise ratio is going to be 0.5. That's the signal power divided by the noise power, which is 0.16. That's a signal to noise ratio of 3.125. And if you turn that into decibels, that's about 4.95 or so decibels. The probability of a bit error is the Q function. This is read from the Gaussian distribution table. Q of 0.5 is our threshold voltage. 0.5 minus 0 divided by the square root of the variance. So that's Q of 0.5 divided by 0.4. So that's Q of 1.25. And now we can go to the table. Our probability of bit error is Q of 1.25. We look up 1.2 and 1.25, and that would give us a probability of 0.1056. This is the probability of an erroneous bit. In analyzing the noise in a pulse code modulated system, it's not as simple as just finding a single bit error. We have other factors to consider as well. First of all, let's look at what we have with our pulse code modulated system. First, we sample an analog signal, and that gives us this sample value M with the subscript K. We're sampling at discrete times, so we have discrete values. So we have this K is an index number to indicate that it's a discrete value. That sampled value is applied to a quantizer so that it is rounded off to its nearest standard value depending upon the number of bits we are using and the number of levels in our quantizer. This quantized value is then transmitted, noise is added, and at the receiver end, a detector determines determines the value for this quantized value, and what then the value that comes out of the detector is potentially different yet still because of detection errors, and this is M with a tilde sub K. Okay, so the quantizer, as we previously discussed with when we looked at signal quantization, it has a range from minus MP to plus MP. So its total range is 2 times MP. We are taking, to meet the Nyquist sampling criteria, we're taking 2 times B samples per second. B is the bandwidth of the original message signal. We are using L levels and N bits per sample. We're turning it into a binary number, so we have to have a certain number of bits per sample. That makes the number of levels always a power of 2, 2 to the power of N. And there is, in the quantization process, always quantization error. And that error is found by taking MK and subtracting M with a hat K. So this is the actual sampled value minus its nearest standard value. The difference between those is the error. At the receiver end, we have detection error. So bits may be misinterpreted as ones or zeros when they're intended to be zeros and ones. And that will lead to a detection error between the input and the output to the detector. And that is, detection error is indicated by this epsilon with the subscript K. And that error is M hat of K minus M tilde of K. Now the total error is found by comparing the input signal on the far left with the output on the far right. MK minus M tilde of K turns out to be equal to the quantization error Q of K, as given by this expression, plus the detection error epsilon of K, as given by that expression. And the two errors are added together. And we're going to look for the power in the error signal. And since the two errors are uncorrelated with each other, then it's simply going to be the power of the quantization error plus the power of the detection error. This is a repeat of what we saw previously with quantization. We'll get the same result for the quantization noise power. I've zoomed in on a bit of the quantizer with L levels. So the spacing between two levels is 2 times MP. That's the total range of the digitizer divided by the number of levels L. So that's the range, that's the spacing between the levels. We have our message signal is the dark line that moves through at a diagonal. At the sampling instant, the value of the message signal is MK, that's the true value. It gets rounded off to the center of the level, that's M hat of K, that's the approximate value. And the quantization error is Q with the subscript K, that's the difference between the two. This error is distributed in a uniform fashion across this range of values. So this is the probability density distribution for, or probability density function for the error value Q. So Q is on the horizontal axis, Q equals 0 is right in the middle, and it ranges from minus MP over L to plus MP over L. That gives a total range of 2 MP over L. And in order to keep the area underneath the probability density function equal to 1, its height is L divided by 2 MP. Okay, so now we can use this probability density function in order to find the average value of Q squared. That would be the noise power. So this is what we're looking at here. It's shown here as a time average, but we're going to take the statistical average of Q squared by plugging Q squared into this integral, multiplying by the probability density function, and integrating over all values of Q, which ranges from minus MP over L to plus MP over L. And when we evaluate this integral, this is our equation. Q squared time averaged is equal to minus the integral minus MP over L to plus MP over L. Q squared times the probability density function time integrated with respect to Q. Probability density function is simply L over 2MP, and we complete the integral. See, L over 2MP is taken out in front of the integration. Then we have the integral of Q squared dq, and the antiderivative is 1/3 Q to the 3rd power, and we're evaluating from its lower limit of integration to its upper limit of integration, and we plug those in. And see, at the upper limit we have MP to the 3rd power divided by L to the 3rd power. And then at the lower limit we've got minus MP to the 3rd power. Well, we're subtracting the lower limit, so we get a minus, and then we get another minus from minus MP to the 3rd power, so that gives us this plus sign. So plus MP to the 3rd over L to the 3rd. Let's see, we add those together. One of the MPs cancels and one of the L's cancels, and we get the quantization noise power is 1/3 MP squared divided by L squared. And this is exactly the same result we got weeks ago when we looked at quantization noise. The detection noise power is a bit more complicated. Let's consider, for example, a 4-bit system. So our input to the detector is a 4-bit word, 1101, let's say. That is a word number K, and that goes into the detector, and out comes a value of the detector, which is the numerical value of 1101. So that's a numerical value of 13. This, of course, would be scaled by the our quantizer levels, our quantizer range, but we'll just leave it here as a value of 13. Let's say, for example, that the first bit is an error. I've numbered the bits 1, 2, 3, 4, 1 being the most significant bit. If that is erroneously detected as a 0 instead of a 1, then the value that would come out of the detector would be the value for 0101. That would be a 5, and we intended to get a 13. We actually got a 5 because of this bit error in detection. So the error in that case would be 13 minus 5 is an error of 8. Now that needs to be scaled by the range of the digitizer, the quantizer, and that's what is occurring here in this last equation. The error is for a bit, depending on which bit you're looking at. So they're numbered from most significant to least significant. So the bit I would be numbered 1, 2, 3, all the way to n, where we have n bits in the word. Depending upon which bit is an error, the value of the error would be 2 to the power of minus I times the total range of the digitizer, 2 times MP. So we can see that this is certainly true if I is equal to 1. 2 to the minus 1 is 1/2. 1/2 times 2 MP would give you a value of MP. So that would be the amount that the detected value would be an error compared to the intended value. If there's an error in the least significant bit, this would be a much smaller value. So this now is the value of the error depending upon which bit is in error. What we want to know is the detection noise power. That's the error epsilon squared and then averaged, and we're shown here as a time average. We're going to do a statistical average. Now again, we have a probability distribution density function, but in this case it's a discrete because we have individual bits. So instead of a summation, instead of an integral, we have a summation over all the possible bits, bit I from 1 to n, and we have the error squared multiplied by the probability of each individual bit. So the total, the expected value of the error squared, which will give us the detection error power, is equal to the summation over I, which is the bit number from 1 to n, times epsilon sub I squared times the probability of that particular bit being in error. Now we're going to take that each bit has the same probability of an error, so P with the subscript epsilon I is a constant value for over the summation, so we can bring it out in front of the summation. So the detection noise power is equal to the probability of a bit error times the summation of epsilon I squared. So using this equation for the detection noise power, and we've determined that the error for each bit is equal to e to the 2 to the minus 1 times 2mp. Now we can plug that in for this term here in the summation. So we get the detection noise power is the probability of a bit error times the summation. And now I have 2 to the minus I times 2mp squared. When you square this, 2 squared is a 4. That can come out in front of the summation. mp squared can come out in front of the summation. Probability of a bit error is in front of the summation. And now we have the summation I equals 1 to n for each one of the bits, 2 to the power of minus 2 times I after we do the squaring operation. So using this equation for the detection noise power, and we've determined that the error for each bit is equal to e to the 2 to the minus 1 times 2mp. Now we can plug that in for this term here in the summation. So we get the detection noise power is the probability of a bit error times the summation. And now I have 2 to the minus I times 2mp squared. When you square this, 2 squared is a 4. That can come out in front of the summation. mp squared can come out in front of the summation. Probability of a bit error is in front of the summation. And now we have the summation I equals 1 to n for each one of the bits, 2 to the power of minus 2 times I after we do the squaring operation. So evaluating the summation, I've written out the terms in the summation starting with I equals 1, then I equals 2, 3, etc. in general, all the way up to I equals n. So we get this summation as listed on this line. Factor out 2 to the minus 2 from each one of these terms, and we get the summation that is listed below. And then turning it back into the summation format, we have a 4 mp squared probability of bit error, then 2 to the minus 2 as a constant times the summation. And we can sum over index m from 0 to n minus 1. And we have 2 to the power minus 2 divided, and I show it divided by 1 because I want to use that on the next slide. All that raised to the power of m. I haven't changed the summation, just manipulated it a little bit. It turns out that a summation from m equals 0 to k of a divided by b to the power of m is equal to this closed form. This is so it's changing a summation to a closed form I don't know what branch of mathematics worked this out to begin with, but we're going to take advantage of this equality. If you let a equal 2 to the power minus 2, if you let b equal to 1, and if you let k plus 1 equal to n, then we'll be able to take this summation in our equation for the detection noise power and replace it with this closed form that's not a summation by making these substitutions. And that's exactly what I've done on this equation. Replaced this summation with this equivalent closed form. And now let's take 2 to the minus 2 power. That's the same thing as 1 over 2 squared. And if you multiply the 2 squared through the denominator, we'll get in this denominator, we get a 1 minus 4, which 1 minus 4 is going to be minus 3. So I've incorporated the minus sign into the numerator by switching the order. We have 1 minus 2 to the power minus 2n divided by 3. And now pulling an algebra trick, multiplying and dividing by the same value, we come up with the detection noise power equal to 4 times MP squared times the probability of a bit error. And then I have this fraction 2 to the power 2 times n, all of that minus 1 divided by 3 times 2 to the power of 2 to the 2 times n. Remember, our number of levels is equal to 2 to the nth power. So if we substitute that back in this equation, we get that the detection noise power is equal to 4 MP squared times the probability of a bit error times the level squared minus 1 divided by 3 times the level squared. If recall, the quantization noise power is 1/3 MP squared divided by the number of levels squared. So the total noise power is going to be the quantization noise power plus the detection noise power. Add those two together and we get the total noise power. And then I do a little algebra. We have a 1/3 in each term. We've got an MP squared in each term. We've got an L squared in each term. So factored out MP squared over 3L squared, and we're left with 1 plus 4 times the probability of a bit error times the level squared minus 1. And if we take our signal power to be the original binary message squared and then time averaged. From this we can form the signal to noise ratio. In the top of the fraction we have the signal power, m squared time averaged, and in the bottom of the fraction we have the total noise power, MP squared over 3L squared times this term in brackets 1 plus 4 probability of an error times L squared minus 1. And with a little bit of algebra, we now have an equation for the signal to noise ratio at the output of our detector. This includes both quantization noise and detection noise. We've got a constant 3 times the number of levels squared times the average power in the message signal. And that's divided by this term. We have a term in brackets, 1 plus and then a 4. We still have the probability of a bit error. That's an interesting twist, times the level squared minus 1. Now, depending upon the binary signaling system used, or using a unipolar signaling, so this probability of a bit error we've determined is the Q function. This is from the Gaussian distribution of A divided by 2 is the threshold voltage divided by sigma n. Sigma n squared is the noise power, so sigma n is the square root of that. Let's see, so I've squared everything and taken the square root inside these parentheses. So we have the square root of a squared divided by 4 sigma n squared, and you factor out a 1/2, so we get 1/2, and what we're left with is we had, for the signal to noise ratio at the input, we had an a squared divided by 2 sigma n squared. That's supposed to be a squared divided by 2 sigma n squared. That was the signal to noise ratio at the output. So now I can express the probability of an error using the Q function and the signal to noise ratio at the input. I'll substitute that back in for this probability of a bit error, and I get this enormous equation, which relates the signal to noise ratio at the output to the signal to noise ratio at the input. And the twist is I've got to use the Gaussian distribution functions table for the area underneath the Gaussian distribution curve to find the probability of an error. Now, this is not something you would want to evaluate by hand. It would be pretty tedious and laborious. Fortunately, it's not too difficult to get a computer to do it. So I set up an Excel spreadsheet so that I could vary the signal to noise ratio at the input and observe the corresponding signal to noise ratio at the output of the digital detector. So I set up a numerical example, took the message power to be 0.5. So this would make this essentially makes logical 1A equal to 1. That would give a message signal 0.5. And also pick the peak range of the digitizer to be 1, just to give a nice numerical value. I picked 8 bits per sample, which means 256 levels. Plug all of those numbers into the equation, and as the signal to noise ratio is varied on the input, we can look at the output signal to noise ratio. Again, I wouldn't want to do this by hand. It would be very tedious, but having the computer do it is not so tedious, and the result is shown after I push the button. This is the noise performance of a binary system with unipolar signaling and 8 bits per sample. Across the bottom is the signal to noise ratio at the inputs. This is determined by the variance of the random Gaussian distributed noise, the value of sigma n squared. That will correspond to a certain signal to noise ratio. It's plotted across the bottom here in decibels. So on the left with 0 decibels, and then all the way up to 30 decibels. On the vertical scale is the signal to noise ratio of the output, also in decibels, starting at 0 decibels and going up to nearly 60 on the chart anyway. Now, remember that a low value for signal to noise ratio is a noisy signal. So on the left, this is noisy. And on the right, when the signal to noise ratio is higher, this would be clean. So that's an N. Could be A, I suppose. R, I mean. So as the input signal ranges from noisy to clean, the output signal also ranges at the bottom. This would be noisy, and up at the top is going to be clean as well. And this is an interesting curve because it accounts for both factors involved in the error of a binary signal. If we have an input that's noisy down here at the bottom, that means there's lots of noise power compared to the signal power. We get bit errors. And those bit errors result in a noisy output signal. See, we are misinterpreting ones as zeros and zeros and ones, and that is simply noise in our output signal. And so that means for a noisy input signal, we get a lot of bit errors and we get a noisy output signal. Now, as the input signal quality increases, that is, as the signal to noise ratio increases and we move left on the curve, we get fewer and fewer bit errors, and the corresponding signal to noise ratio at the output increases as we move up this curve. And but we reach a point somewhere when the input signal to noise ratio is high enough, that is the noise is smaller and smaller compared to the signal, so that the number of bit errors and the probability of a bit error drops down essentially to zero. And at this point, the probability of a bit error has dropped to zero, essentially. But we've still got the quantization error that we can't get rid of. So it levels off at this level that represents the quantization error. This is the quantization error. I don't want to spell out quantization or error. And you'll notice that it is a constant value. For 8 bits per sample, that turns out to be just about 50 decibels. And it does not matter how clean the input signal is above a certain threshold. We always have a constant quantization error of about 50 decibels in this case. So this curve shows the two forms of noise in a digital signal and where each form of noise dominates. The bit errors dominate for a noisy input signal, and after the signal to noise ratio rises to the point where there are essentially no more bit errors, we are left with the quantization error, which is a constant and does not change even with a better signal to noise ratio at the input. Just for illustration purposes, I ran the same Excel sheet for various numbers of bits per sample, and they all have the same kind of shape. The curves have the same kind of shape. Here's the signal to noise ratio of the input signal in decibels across the bottom. Noisy signals on the left with a small signal to noise ratio, clean signals on the right with a high signal to noise ratio. Again, when the signal to noise ratio of the input signal is low, the response is dominated by bit error. That's to the left of a certain threshold. And then there is a threshold value where the probability of a bit error essentially drops to zero. And what we are left with is the quantization error. I'll make that QE for quantization error. So on the left-hand side of the curve, we've got BE for bit error. And on the right-hand side, this is QE for quantization error. And depending upon the number of bits you choose to use in the quantizer, you will get a different quantization noise signal a different quantization noise output in decibels, or signal to noise ratio in decibels. And these values match precisely the values we found when we analyzed the quantization systems earlier in the semester.